Okay, so good evening, everyone. My voice is audible clearly. Can someone confirm?
Yes, sir.
Okay, and the screen is visible.
Yes, sir.
Yes, sir, it's visible.
Okay, so I'll just give a quick recap of what we had talked in the last class, and then I'll move on to today's class. So last class we were basically talking about the different numerical techniques to solve the nonlinear equations. There we started from the basics. Prior to this, we had seen the different techniques to solve the linear equations, where the equations were of the form of ax equals to b, and then using the matrix approach and different other techniques, we saw how to solve those equations. However, if the equations are not linear, those techniques fail to operate, and hence we have some dedicated techniques, dedicated numerical methods to solve the nonlinear equations. So basically, any equation, to understand that, I first describe the basics of that. So any equation is made up of a number of variables, and this number of variables form an expression or a function. And when this function is given with some particular condition, then we call it as an equation. So an example of a nonlinear equation will be like I have shown here. It is x cos x plus 1 equals to 0. So x is basically a variable, whereas cos x is a function. So combination of these basically gives me x cos x plus 1, which is an expression. And I'm putting a condition on this expression that this needs to be equals to 0. So this is called a equation. So in order to solve these nonlinear equations, we don't have any standard analytical techniques to solve these kind of equations, unlike the linear equations. Here we have to take help of the nonlinear numerical methods or numerical techniques. Like there are two types of basically two classes of numerical techniques to solve these nonlinear equations. First one is the bracketing method, and the second one is the open methods. I'll describe what is the difference between this bracketing method and the open methods. So basically, in this bracketing method, your root will be an interval will be given to you, and your root will lie within that interval. So basically, your root is being bracketed by that interval. We say a root is being bracketed by that interval. That's why it is called a bracketing method. Whereas in open methods, we have an initial guess to the solution. We don't have a interval or something of that kind. So those are open methods. In bracketing methods, we have the bisection method and the method of false position, which is also called as the regular falsy method. Whereas in open methods, we have the fixed point iteration method, the Newton-Raphson, the well-known Newton-Raphson method, and the secant method. So last class we had discussed about bisection method, secant method, and regular falsy method. These three we had discussed, and I had shown you the MATLAB code for bisection method and secant method. And I asked for the homework, I'd asked the MATLAB code of the method of false position. So today we will be first again looking into all these methods, and most of you have not submitted the homework. That's fine. I'll discuss the MATLAB code for the method of false position also, and then I'll move to the fixed point methods and the Newton-Raphson method. So in fixed point and Newton-Raphson method, we will see how we can solve single variable as well as multivariable equations. In both Newton-Raphson and in fixed point methods, we'll be seeing that. So once we cover all this, that will basically end our third module, which is the nonlinear equation solving using numerical techniques. Then, if time permits today, we will move to regression techniques, the linear regression, how to linearize a nonlinear data, all those things we will look into. That basically does not have much of MATLAB there. Then after that, we'll move to numerical interpolation, where we will have a lot of MATLAB codes. Following after interpolation, we will see the numerical differentiation, numerical integration. Then finally, we will end with the ordinary differential equations. And if time permits, I'll discuss the numerical techniques to solve the partial differential equations also. Okay, so just a quick recap of the basic technique to solve any nonlinear equation is by the graphical approach. So if we have a equation of the form of fx equals to 0, what we do is we subdivide it into two different equations, y equals to fx and y equals to 0. Then what we do, we plot this y equals to fx graph in the graph paper. And so what it basically means is y equals to f of x and y equals to 0, right? So fx equals to 0 is obtained by the intersection of these two equations. So this, in order to find a solution for f of x equals to 0, what we can do alternatively is we can plot these two graphs separately, y equals to fx and y equals to 0, and then we can find the intersection point of these graphs. So that will basically give me the solutions of the equation. So here I have drawn a random function, and y equals to 0 is the x-axis, right? So we often tell that the roots of an equation are the intersection points of that graph of the plot of that equation with the x-axis. So why we tell that? So what is the rationale or what is the logic behind this? So just a second. Okay. So this is the logic behind telling that the intersection points of a function with the x-axis gives me the roots of the equation. So here are the different roots of the equation which I have shown here. So there are multiple roots of this equation. So there can be three different cases, right? There can be a no solution case, there can be a unique solution, that is a single intersection point, and there can be multiple solutions like as I have shown here. So when is the no solution? So if you have a graph like this, the red one shown here, it doesn't intersect with the x-axis at any point of time. At none of the values of x, it intersects with x-axis. So we say that it does not have any solution. Fx equals to 0 does not have a solution. And the green curve here, it intersects the x-axis at a particular point, at a single particular point, and then we called it to have an unique solution. Okay. So this is a very crude technique or the basic technique. If you don't know anything, you can use this technique and you can find the solution of that equation using a graph paper. So now we come to the generalized techniques. First one is the bisection method. So what we do in bisection method is, in bisection method, the equation will be given to you and you will be given an interval. Like here it is given that fx equals to x cos x plus 1, which is equals to 0. You have to solve this equation, and it is told that your root lies within the interval minus 2 comma 4. So once this is told, this is known as the bracketing, because your root, it lies between these 2 points only. That's why it is called a bracketing method. So now first, if we try to see how is the this thing, the graphical interpretation, if we try to see. So suppose this green curve here is the plot of the equation. It's a random plot I have made, and you mark these 2 points, the two intervals, that is minus 2 and 4. So here is minus 2, and here I have, I'll mark with red. Here I have 4, here I have minus 2. So what does bisection method tell me? Bisection method tells me that you constantly try to shrink the interval such that at every point, at every iteration, you bisect the interval. That is, your limit is between minus 2 and 4. So you find the midpoint of that. What is the midpoint of minus 2 and 4? It is 1, right? Then you find out the value of the function at that midpoint. So if we draw a vertical line, this dotted line, here the intersection point of that with the graph of that equation gives me the functional value, right? So here the functional value is greater than 1, greater than 0. That is, it is a positive number. So what does that indicate? If it is a positive number, it indicates that your root has to lie between, initially first it was lying between minus 2 and 4. Then what we did, we bisected the interval. So now here it is 1, right? So now you have two sub intervals, minus 2 to 1 and 1 to 4. So in order to shrink the interval, either your root has to lie between minus 2 and 1 or between 1 and 4. So now how to decide what is my next sub interval? Is it minus 2 to 1 or 1 to 4? So that will basically be decided based on the functional value of f of c. That is functional value at the midpoint. If it is positive, then your lower limit will change. That is, your root will now lie between 1 and 4. If this f of c is negative, your upper limit will change. That is, now I will consider only minus 2 to 1, not 1 to 4. So why we are doing this, the logic behind this is, see, if a function has to have a root at a particular point, we know it has to be 0. That is, it should the functional value of that particular point should be 0. So now just imagine like this. You have a graph like this, and suppose this is my root point. So what will happen before and after this root point of this function? So either it can be before the root it was positive, and then after the root it turned to be negative. Or it can happen either before the root it was negative, after the root it is positive. So that is, at the point of intersection, at the root point, your function has to change the sign. That is, see here, this initially my first interval was minus 2 to 4. So at minus 2 my functional value is positive, whereas at 4 my functional value is negative. So that means that yes, my root can lie between minus 2 and 4. However, when it changes, that is when you bisect this interval, you have 2 points now, minus 2 and 1, now 1 and 4. In 1 and 4 you see, at 1 it is positive, 4 it is negative. So yes, your root can lie between 1 and 4, but not between minus 2 and 1, because your functional value at minus 2 is positive, at 1 it is also positive. So your root cannot lie between these 2 points. That is, at the root point, if you consider a particular interval, there has to be an opposite sign in the functional value. So this is the logic or the rationale behind changing the subinterval at every point of time. So the logic is like, at every point you take the midpoint of the two intervals, you have two subintervals, then you choose the correct subinterval for the next iteration. Then again you repeat the process. How do you choose the next subinterval? It is basically based on the functional value at those two particular points. Wherever there is a sign change, you have to choose that particular interval, not the other one. Is it clear?
So I have a question here that
Yes.
what if we have multiple peaks and the valleys in the given interval? Like say in this interval minus 2 to 4, I have multiple peaks and the valleys of the given function. Then
Okay, I understood your question. You are telling like this, right? You are telling like this. Like this you are telling, right?
like this, or there could be other form also, like say inward being minus 2 and so you pick the first subinterval as say minus 2 to 1. So
Hmm.
inward being minus 2 to 1 also, there could be say, this function might be crossing the x-axis multiple times, say in this interval,
Yeah,
and
yeah, I
similarly from
understood.
1 to 4 onwards also.
So that will be based on the interval. Like here you have chosen the interval as minus 2 to 4. So within that interval, this numerical techniques, later on also we will see in Newton-Raphson method also, we'll be seeing that based on the initial the interval which you have chosen, you can only guess one particular root. If it has multiple roots, this method fails. It cannot give you all the roots. It will give you only one particular root. This bisection method or the what all methods we'll discuss, that will give you one particular root, and we don't know which route it will give. It will be based on the initial value that you are choosing there, or the interval that you are choosing. I'll look into this once again and I'll get back to you.
Okay, yes, and
Yeah.
there could be, I was thinking of one
Hmm.
another scenario also. So,
Yeah.
what if, is this necessary that we would be getting, we would be deciding one out of the two subintervals. So, can this ever happen that in the first subinterval also we are getting this combination of positive and the negative values of the function, and similarly in the second subintervals also, I do have the same combination of the
Hmm.
positive and the negative values of the
Uh, I
function.
don't. I don't think this will happen because if you have one particular root or unique solution, if you have to a particular equation, then I don't think this will happen. Uh,
Oh, I see. So I see. I see. So is this necessary that, I mean, whichever function we are considering here are going to have a unique solution in the given interval?
yeah, that's what I was telling. This bisection method and most of these numerical techniques, this means it compulsorily has to have one unique solution, then only this method will work. If you take an equation which has multiple roots, it will give you only one solution. It will not give you the other solution. If you choose a different initial guess, then it might give you the other solution. So I'll show that in the
Oh,
Newton-Raphson method also.
okay. Okay. Yes. Yeah. Now I understood. Yeah. Thanks. Yeah.
Yeah, thank you. So this is the logic behind this choosing these different subintervals. So here I've just shown you tabulated the values for you. So this was about the bisection method, right? So here first one iteration I'll show you. See, if first it was -2 and 4. At -2 it was the functional value was 1.83 and functional value at 4 was -1.61. We subdivide the interval, that is the midpoint we find out, which is 1. We find out the functional value at f of c, that is 1, f of 1, it is 1.54. So now your limit will change since it is greater than 0 and your f of 4 is less than 0. That's why your limit will now change to 1 and 4. Again, we do the same thing. Again, we see that here it is negative. Now again, since it is negative and your so it has to be 1 and 2.5. In this way, we will slowly will shrink the interval. First it was -2 to 4. Then we are saying 1 to 4. So when will it converge? You can ask. There are two convergence conditions here. Any one has to be satisfied. Both will be satisfied together. Either at the root point, your f of c. So your root is at the end of the iteration. C is your root. That is the midpoint. So your f of c has to be almost near to 0. Or what you can see is if you are shrinking the interval, your both a and b will also merge at one point. So if you see either a and b, if they are very close to each other, then also you can stop your iteration. It is the same way of seeing the same thing in two different ways we can think of. Either your a and b has to almost merge, that is the difference between a and b has to be very negligible, or your functional value at c will be 0. Okay. So from this we move to the second method. So I'll not discuss this one because you can see the recording. I'll go to today's class, otherwise I cannot finish it. So you can just check the recording and then you can come back to me. I can discuss. We can discuss. Okay. So now, okay. First we will see the MATLAB code for this regular falsy method. So for that I'll just give a quick recap of the regular falsy method. Okay, so this was our regular falsy or the method of false position. So what we did here basically is this blue line is the curve of the equation, and we will be given two intervals, that is XL and XU. So instead of bisecting here, we are trying to find a more efficient technique to find out the middle point, not the middle point, a point between XL and XU. So in bisection method, we were fixing it as the midpoint, and then we were changing the intervals. So here we can use the property of similarity of the triangle. If you see these triangles, triangle ABC and triangle DEC, these two triangles are similar. Based on the angle conditions and something, we can find out the similarity. Then if it is similar, we can say the ratio of the corresponding sides are equal, right? So DE by AB will be equals to DC by BC. So if we substitute, what is DE? DE is f of XL, and your AB is f of XU, that is XL and XU. So f of XU, DC is XR minus XL, and your BC is XU minus XR. So if we substitute this, we can find out a formula for XR, that is the point in between XL and XU. So XR is equal to XL into FXU minus XU FXL by upon f of XU plus f of XL. So if we see this is not the midpoint, right? Similarly, in secant method also, if you see, we have an expression for this. So what we do is, we are given with XL and XU. Using this equation, we try to find out XR. Then we again find out the value of the function at XR, and we see where there is a sign change. Then accordingly, we choose the next interval, just like bisection method. Okay. So I'll just, this logic is clear, right? So I'll show you the MATLAB code for this. So I have taken a random function here, x to the power 2.5 minus 12 x power 1.5 minus 20x plus 120. So error value first I have taken as a random. Is my screen visible? The MATLAB screen?
Not yet, sir.
Okay, okay, sorry. Just a second. Now is it visible?
Yes, sir.
Okay. So in this, we can see here, first I've declared a symbolic variable, then I've defined the function. This you can take as input also. I've directly defined here. So, and your error value, I have taken a large value. You can take anything for initialization. It is 1. And the lower limit and the upper limit, XL and XU, we have taken as 0 to 10. Then we have I have taken to mark the number of iterations. I have taken k is equals to 1. I'll just add the comment here. It is basically to track number of iterations. So now I am checking whether this absolute value you have to use. Otherwise, if the error is negative, then it will not work. So absolute of error is greater than some tolerance limit I have taken. And then what we do is we have to find this XR, right? What was XR? F of XL, sorry, XL, F of XU minus XU, F of XL upon F of XU minus F of XL. So first line, we are substituting this function in place of X, we are substituting XL. So this is F1. Then F2 is a function with in place of X, we are substituting XU. Then we are finding out XR using that equation. Then at XR, what is the functional value we are checking? If it is F3. So if F3 is greater than 0, then we are changing the limit to XL, the lower limit we are changing, that is XL is now XR. Otherwise, if it is greater than 0, then we are changing it to XR, that is XU equals to XR. And then what is the error now? What should be the convergence condition? This F3 should be equal to 0, right? So error we are keeping as F3. It is not correct to call this error, or you can call this as a final value. So k, every time we are increasing the iteration, k equals to k plus 1, and finally we are printing the root obtained is this one in these iterations. So I'll run this code. So you can see here this root obtained is 3.34 in 5 iterations. Similarly, if I run this bisection method, you can see here, just remember in regular false it was five iterations, right? So I'll just change the equation here, or I'm trying to compare both these functions, and then we'll see all these methods, and then we can find which one is more accurate, or which one is more faster. We can see that. So, so just remember in regular falsy we got it in 5 iterations. Okay. So I'll take the same tolerance. Only I've taken 1, 2, 3, 4. So minus 5 I've taken. So you can see here root obtained is almost same, but it is taking in bisection method, it is taking 20 iterations. So this, and the second method, if you see, just copy it. So 3, 4, okay. Sum of 1 is 0. So this one you can see it is in 9 iterations. So you can understand the order of fastness or order of which one is faster and towards convergence. Your method of false position is the fastest. All these methods are using the same concept. Is my screen visible? The MATLAB screen?
Yes.
Okay.
Yes, sir.
Okay. So, so you can understand all these methods, the bisection method or the regular falsy or the secant method, all are using the same concept. However, what is the difference? In bisection method, we are choosing the intermediate point just by bisecting. Whereas in secant method, we are choosing it by the slope of the tangent. You can see. And in false position, what we are doing is we are using the property of similarity. We are trying to exploit the property of similarity of triangles, and then from that we are trying to find out an intermediate point, and then based on the functional values we are changing the limits. So you can understand that this different methods you can use it, but this bisection method is the slowest or the most crude method, whereas the secant and the false position methods are more sophisticated methods. Is it clear?
Yes, sir.
Mr. Goel, is it clear? Can I proceed?
Yes, yes, it is clear to me.
Okay, thank you, sir. Will now share this screen, the notes screen. Okay, so sorry. One more thing was there, no? The Gauss-Seidel method. I think any one of you have submitted the homeworks? Only 2%. Okay, fine. Okay, Gauss-Seidel method I'll discuss at last. Now let me complete these topics. Then we'll discuss Gauss-Seidel method. Okay, so today we will be talking about, first we will be talking about one method which is known as fixed point iterations. So first we'll be looking into what do we mean by fixed point iterations, and then we'll be seeing the two variants of this method, which is one is single variable fixed point iteration method and the other is a multivariable fixed point iteration method. So you can stop me any point if you want any clarifications. I'll just start. Okay, so this is not a bracketing method. This is a open method. So open method. What do you mean by open method? To compute solution to f of x equals to 0. So here there will be no interval of roots, or rather it will be given as a single value, right? So what is the, first I'll just give you a quick outline of the algorithm, then I'll take an example. What is the algorithm? So you will be given, input will be f of x will be given to you and your one initial value will be given to you, that is x of 0. These are the two inputs. Now in the first step what we will do is we have to rewrite this fx equals to 0 as x equals to g of x. So just first try to understand. Once we see the example, it will be clear to you. So we have to rewrite that equation as x equals to some function of x. This is known as the iteration function. So this we call as function b. This we call as function a. So if we can do this, and then we can find out the intersection point of these y equals to g of x and y equals to x. A point of intersection of y equals to g of x So a point of intersection of these two functions, that is y equals to x and y equals to g of x, will give you your solution, right? Will give the solution. So because fx equals to 0, that function we are trying to remodel or rewrite as x equals to g of x. Now what we do is we draw the line y equals to x and the function y equals to g of x. And then we try to find out the intersection point of these two functions. So if we can do that, then the intersection point will be known as the fixed point. This is our fixed point, and that will give me the solution of the original equation fx equals to 0. So this procedure will begin with an initial guess. The procedure begins with an initial guess, which is x1 near the fixed point. So fixed point is the intersection point, right? Near the fixed point. So how will we proceed? Next point we have to calculate in the iteration, which is x2, that will be given by g of x1. Similarly, next point x3 will be given by g of x2, and this will be continued till convergence is achieved. So now we'll see one example. So the process I'll just repeat once again. So what we do is we rewrite this fx equals to 0 as x equals to g of x. So now we have two functions, function A and function B. Function A is y equals to g of x, and the third function is second function is y equals to x. What we do from the graphical approach, what we can do is we can plot these two functions and find out the intersection point. So that intersection point will give you the original root of the original equation fx equals to 0. So now in the iterative technique, what we do, we'll be given a initial guess to the solution which will be near that solution. So using that initial solution, we find out the next point in the solution, which is x2. x1 is the initial solution. x2 will be given by g of x1. Then we'll see x3 equals to g of x2. Similarly, we will continue till convergence is achieved. So now there are many questions on this. So this process is known as recasting. Okay. This process of reforming the equation fx equals to 0 as x equal to g of x is basically called as recasting. Just a second. So what is this concept of recasting? Suppose you are given some f of x, you are given, which you have to find the solution. I'm taking a simple function first. No, not this one. We'll take x minus 1 by 3 e to the power x. Okay, so this is our function which is given to us, and we are given as x of 1 equals to 1.25. So now if we want to use the idea of recasting, so if we try to find out this function in the form of x equals to g of x, what we can do is there are two possibilities. We can either write as x equal to e power x by 3, or we can write as if we take ln on both sides, ln e power x is x, right? Ln of 3x. This is one possibility. One more, many infinite possibilities are there. We can write it as x equals to 2x minus e power x by 3. So there are multiple other possibilities also we can think of. So these are the three different recasting options which we have. This is one, this is one, and this is one. So now each one we will see that then we'll try to find out uh, which recasting function we need to use. Okay. So first we will look into the first option, which is the most obvious one, which is x equals to e power x by 3. So x of 1 is given to me as 1.25. From this we can find out x of 2, which is e power 1.25 by 3, which will give you 1.163. X of 3 equals to e power x of 2 by 3, which will give you 1.066. Similarly, if we consider like this, and I can show you in the MATLAB, we will up if we do up to 20 iterations, we'll see this will converge to 0.619. Okay, so now if we just plot this function also, all right, I'll show you in this MATLAB only, that is better. Is the MATLAB screen visible
Not yet, sir.
now?
Yes, sir. Yes, sir.
Okay, I'll just do it in the command window only. So what we want to do is we have x equals to e power x by 3, right? X of x by 3. Clear everything first. Sims of x. We are taking some x1 x by 3. Okay. Now in code, first we'll just init error as 1. Will while error is greater than 1 e minus 6, we will write that and this. Okay, solution given as 1.25, right? And error is given as, I'll take as 1, while error is greater than 1 e minus 6. K will be to track the number of iterations. K will take as 1. Then we'll take while error is greater than 1 e minus 6. So all of a plus 1 will be equals to substitute of function, that is x1 I have taken, comma, so all of k. That is in place of x, will substitute this k equals to k plus 1. I'll just copy this, write it in a script file. And error we have to calculate f of sol of k plus 1 sol of k by sol of k minus 1. Just give me one moment, I'll do it. So you can see here, I'll just print it also. Solution option is so you can see here the solution obtained is 0.619 in 32 iterations. So I'll just plot this function and show you what was my original function. It is x minus e power x by 3, right? So I'll just take t as minus 0 to 0 to 5. I'll take 2. I'll take, and I'll take xx equal to exp of dt not by 3. If I just plot this function, figure plot xx. So if you see this, sorry, x minus so you can see here, okay, I'll draw this x-axis also. So you can see here the x-axis intersects this function at 2 points, right? One is around 0.619 and another is some value between 1. Okay, I'll just check what is it. It is some 1.511 and another value is around 0.62. So you can see here, if I run this code, it is giving me one solution. You can see it is giving solution obtained is 0.619 in 32 iterations. What about the other solution? So this is what I was telling. This methods will give you any one solution at a time. So now what I can change? This function that is which we wrote as our original equation was x minus e power x by 3. So that we changed and wrote in the form of x equals to e to power x by 3. So that was my first option. What was my second option? It was x minus e power x by 3 equals to 0 if we write it as x equal to ln of 3x, right? So if we just change here and change this recasting function as ln, that is log of 3 into x, and we'll see whether we are getting any solution here. Okay. Here also we got, see, solution obtained is 1.512 in 30 iterations. So now it is giving me the other solution when I change this recasting function. Now what I will do is this initial value I will change to say some 10. Now we will see whether it is giving me the solution again. It is giving, but but this function, it will not work, I think.
So there are two solutions.
Yes.
There are two solutions. Solution one line
What you are telling? Can you come back again?
line 11 and sir, please show
Huh?
the code. Show the
Okay.
code, sir.
Yes.
Uh, line 11 and line 8 same.
Oh, that's why. Sorry. Sorry. See, now the number of iterations is changing. That is, if I take it some other value, I think this is this, it will work. This function, it will work. That's why it is not. I'll show you another one where based on this initial value also, sometimes it will not converge. So you can understand at least based on this recasting function, that is line number 10. First I had used e power x by 3. Then I changed it to log of ln of 3x. So one more option was there with me. I'll just check it. 2x minus e power x by 3. So this is giving me in less number of iterations. I think, okay, less number, it is giving, 1 second. I'll just clear everything and then see. Okay, I'll just change this one, initial value. See, this one you can see. Now it is giving me such a huge value. So why is it giving me? So this means that your solution is not converging. That's why you are getting some junk value here. And in 3 iterations, it is giving me. So you can understand here, this is what I was trying to tell to you. Based on the initial guess, this is the initial solution, right? Based on the initial solution and this recasting function, your solution will depend. So here it is diverting, or it is totally out of my actual solution. So you can see here, if I just see what are the values of the solution I got. See, I got some in the order of 10 to the power 43. So it is clearly visible that it is diverging. Is it clear to you, or should I explain it again? Is the code?
Yes, sir. Clear.
Okay. Any questions, any doubts from anyone?
So, I mean, this
Yeah.
idea of recasting is pretty interesting. So, are there rules of recasting a function, or I mean, how to view this recasting thing that we replaced x by gx, and then we or we did something else in the recasting? What we did
Okay.
basically?
I'll just tell, sir. I'll just share my screen and I'll tell you.
Yes, yes.
Just a second. So here what I did is, so this was my original equation, right? So we were
Yes.
asked to find a solution to x minus e power x by 3 equals to 0. And we were given the initial guess as 1.25. So based on that, we tried to express this equation rather in the form of x equals to g of x equals to some function of x. So there can be infinite number of possibilities to do this. So first option was we did it as x equal to e power x by 3. Next option was we did it like this, x equal 3x equals to e power x, and then if we take ln on both sides, again we can get x equal to ln of 3x. The third possibility was like this, x equals to 2x minus e power x by 3. So this is my recasting function, right? G of x here, or here this was my recasting function g of x. Next, first case, this was my g of x. So what I did is then using this recasting function and based on the initial solution, we tried to fix. So why is it called fixed point? Because first we are taking an initial guess and we are fixing that point. Based on that initial guess, we are trying to find the value of the solution at subsequent steps. So in the MATLAB code, I showed you with all these three functions, and I showed that all these three functions, if we are taking the initial guess correctly, that is, if it is near to the original solution, then it is approaching to the exact solution, but there is a difference in the number of iterations it takes to converge to the solution. So that this is the concept of recasting, that we can express it as x as any g of x, but there is no hard and fast rule. We don't know, by trial and error only we have to see which one is giving me a solution or convergence in lesser number of iterations or faster. So I'll show you another example where you can see based on the recasting function also your solution can diverge. So as I showed you, for this one I think x equal to ln of 3x, if I am taking the initial value as some random value, say x of 1 is taken as some 1000 I took, and I showed you that it is diverging completely, and we are getting some junk value that is of the order of 10 power 43 or something like that. So this actually shows that your convergence depends on two factors. One is the choice of the recasting function, and second is the initial guess. Now you can ask me, is there any hard and fast rule on what g of x I should choose? No, there is no hard and fast rule. Based on your trial and error only, you have to select this recasting function. Is it clear?
Yes, yes, I understood. Yeah, thanks.
Yeah. Just a second. I'll take a 5 minutes gap. I'll 5 minutes break and then I'll come back. Okay, so we'll start. My audible?
Yes, sir.
Okay. So as I was telling, so the choice of this recasting function and the initial guess of the solution will determine whether your solution is converging or whether it is diverging, or whether convergence is achieved or not. So basically convergence will depend on two factors. One is the choice of f of x and second is the initial guess. So I'll just write it down. Convergence basically depends on, number one is choice of f of x, that is, sorry, choice of the recasting function, and number two is the initial guess of the solution. So these two factors will determine the convergence, in how many iterations you will converge, or whether you will at all converge or your solution is diverging. So this is all about the fixed point iteration method in the single variable fixed point iteration method. So now we'll move to the multivariable fixed point iteration method. There also similar kind of thing is, I'll just give an example and we'll quickly complete this. It is basically multivariable fixed point iteration scheme. So if we look into multivariable fixed point iteration scheme, so basically we will have two variables, right? Two variables and two unknown variables for which we have to find the solution, and two equations will be given to you. So I'll take one example. First equation is 4 minus 8y2 plus 4y3, and second equation is 1 minus 4y2 plus 3y3 plus y3 square equals to 0. So these are the two equations, and the two unknowns here are f y2 and y3. And your y vector is the initial solution is given to you as 0.5 and 0.5. So this is given to you, and based on this, you have to find out the solution to these equations. So what we will do is, first step, we have to form that x equals to g of x type of recasting function here also. So in single variable, what we were doing were x equals to g of x, right? So here, there the unknown variable was x. Here there are two variables, x1 and x2, or y2 and y3 here. So from first equation, we'll try to find out the first recasting function, that is y in the form of y2 equals to g of y2 from the first equation, and from the second equation, we'll try to find out y3 equals to, sorry. So here the thing is, this g will be both function of y2 and y3. And y3 will be again g of y2 and y3. Then we will carry on our process, that is y2 of, this is y of 1 is given to you, y of, from the first equation we will try to find out y2 of 1 comma y3 of 1, and from the second equation we'll try to find out y3 of 2 equal to g of y2 of 1 comma y3 of, this will, and this will continue until it converges. Y2 of 3 will be g of y2 of 2, y3 of 2. So like this we have to continue.
So will this g or the form of the function be same for both y2 and y3, or will they be
No, it
different?
is, sorry, I have written it as same. It will be different, obviously, because the equations are different. This is what you are
Yes.
telling, right?
Yes, yes, yes.
Yes. So it will be two different functions we'll get, and there we have to substitute G1 and G2. Okay, so we'll see this example how to solve this. So the first equation is 4 minus 8y2 plus 4y3 minus 2y2 cube equals to 0. So there can be again infinite number of possibilities. I am doing one possibility, the easiest one. From this 8y2 I am doing. So it is basically 4y3 plus 2y2 cubed minus 4 upon 8. If we simplify this, we'll get as y2 equals to 4. So we'll get y3 by 2 plus y2 cubed by 4 minus 1 by 2. So this is my first recasting function, which is g1 of y2 comma y3. From this we have to find out y2 of 2. So it is basically y3 of 1 by 2 plus y2 of 1 cube by 4 minus 1 by 2. So if you substitute this one, y3 of 1 and y2 of 1 both are 0.5, right? So if you do this, y3 of 1 is 0.5. So it is 1 by 4 plus 1 by 8, 1 by 32 plus 1 by 2. So if we do this, 8 plus 1 minus 6. So it is basically minus 7 by 32. Similarly, y3 from the second equation, from equation 2, we'll get y3, right? So I'll first write down the equation. The equation was 1 minus 4y2 plus 3y3 plus y3 square equals to 0. From this, if we try to find out y3, it is 4y2 minus y3 square minus 1 upon 3. From this, we substitute as y3 of 2, 4y2 1 minus y3 1 square minus 1 upon 3. So 4 into half is 2 minus y3 of 1 square 1 by 4 minus 1 by 3. So this will give me 4. This will give me 1 by 4. So at the end of the first step, you get your y vector as minus 7 by 32 and 1 by 4. Again, this is the first step. Then again, we have to repeat these steps. So this is your homework. You have to write a MATLAB code for this. Write a MATLAB code for multivariable fixed point iteration. So is this concept clear? And we'll stop this iteration when the consecutive values are almost equal. That is, it is within the tolerance limit. Is this concept clear? Any doubts? Any confusion? Any doubts, anyone?
This is clear.
Okay. So this is all about the fixed point iteration method. Both single variable and multivariable I have discussed. And now we will move to the second topic, which is Newton-Raphson method. Just a second. In Newton,
So
yes.
yeah, I have a query here. Then what if in the function I have a combination of say algebraic and trigonometric functions. Like in the beginning of, this subject in the very first lecture, you talked about some of the functions and which is difficult to compute. And and I remember that you named those function as something transcendental, something you
Yes.
mentioned. So what if the function, the argument of the functions, are the combination of say algebraic and the trigonometric functions? Then how to use this idea of the recasting then?
No, there we cannot use the idea of recasting. Okay, I'll just take one example. Like if we have like this, say cos x minus x equals to 0, if we can do it. However, if we have, you're telling cos x minus log x equals to 0, if you have, then also we can do it, I think. Oh, we can do it. We can express it in this form, right? Any kind of function. Can you give me an example where we cannot do, you think?
I don't remember the exact function, but then in the beginning of this subject,
Hmm.
while giving the overview of the importance of the iterative functions, you gave some examples and wherein it is difficult to compute the exact value. And someone said that we cannot get the intersection of x and log x.
Yes,
That
that is correct.
Yeah,
Uh, okay, I'll check that and I'll get back to you.
yeah, sure, yeah. Thanks.
Hmm. Okay. So, what I was discussing about Newton-Raphson method, right? So, in Newton-Raphson method, it is again another open method. That is, you will be given a initial guess to the solution, not a limit, not an interval, right? Open method to solve. And okay. So here one condition is there. In order to solve the equation by Newton-Raphson method, the first order derivative of the function, that is f dash x, first order derivative of the function, that is f dash x, should be continuous in within the entire real number interval. Because we are using the derivative of the function here, it has to be continuous. There should not be any discontinuity in the derivative of the function. If there is a discontinuity, that equation or that function cannot be solved using the Newton-Raphson method. So we'll see why. First, we'll see the graphical interpretation, which will make it more appealing. Have So if you have a function, say like this, I'm taking a random function. You have a function like this, right? And you're given an initial, you know from the plot that this is your final root, right? But you are given an initial solution, say at x1 here. This is your x of 1, x1 I am taking. So what we do basically, from this x1, we have to approach towards this actual root, right? So what we do is, at the initial value, we find out the value of the function at that initial value. Then we draw a tangent at this point. So if I draw a tangent here, may not be exactly correct. It will be something like this. It will be something like this. So this is the tangent to this curve at this particular point. So what we do, we extend this tangent till it intersects the x-axis. So say it intersects the x-axis at some point, say x2. So this x2 is my next solution. That is, from x1, we approach to x2. Then what we do is, again we repeat the same process. We find the value of the function at that particular point. Then we again draw a tangent at this point. If we draw a tangent and then again extend it here, we will achieve we'll approach at the next point, which is x3. So like this, again, we repeat the same thing here. Again, from x3, we draw a vertical line, that is, we find the functional value, and then we approach towards the solution. So this is the graphical interpretation of the graphical approach behind understanding the Newton-Raphson method. Is there any doubt here? Anything you want to clarify?
No, sir.
So now, how to do it mathematically? That is, you need to have some iterative formula to find out the solution, right? X1 will be given to you. How to find out x2 from x1? Then how to find out x3? So you need to have an iterative formula. So from this graphical thing, we'll try to derive that formula. So if we find out what is the equation of the first tangent, equation of the tangent. So this tangent passes through this point, right? What is the coordinates of this point? X1 and f of x1. And what is the slope of the tangent? It is f dash x1, right? So if I write the equation like this, y minus f of x1 equal to slope is f dash x1 into x minus x1. So this is the equation of the tangent, right? The first tangent I'm talking about. So now what you need to do from this tangent, you need to find out x2, right? So what is x2? x2 is the value of x from the tangent equation when y is 0, right? So now if we substitute y equal to 0, then your x is equal to x2. So if we substitute here, minus f of x1 equals to f dash x1 into x2 minus x1. From this, we can find out x2 as x1 minus so this is the iterative formula. So this is for the first tangent, right? Similarly, if you repeat the same thing for the next tangent, you will again get x3 equals to x2 minus f of x2 by f dash x2. So like this, you can find a generalized formula for this, right? So it is xk plus 1 equal to xk f dash of xk. So this is the generalized formula. Is this clear how this uh, iterative method? Is it clear?
Yes, sir.
Okay. So what we'll do is we'll see the corresponding MATLAB code for this. Is the screen visible?
Not yet, sir.
Now is it visible?
Yes, sir.
Okay. So you see here in Newton-Raphson method, what we are doing is First, we are declaring the function in line 7. Then we are differentiating the function. In MATLAB, you have a command which is for diff of, if you give function comma x, it will differentiate the function with respect to the variable which you give here. So the first initial value I am taking as say 1000. Okay, 1 second. I'll take the proper value rather. So say the first value, the sol is the array for the solution, and this is my first initial value which I am taking. Error I am taking as any value 1, and the number of iterations I am starting from k equals to 2. Okay. So I need like xk plus 1 is equal to xk minus f of xk by f dash xk, right? So just you can do this here. Since I have taken k equals to 2 here, that's why I am substituting sol of k minus 1. If you take k equals to 1 here, you can do directly k. So f1 is the f of xk and f2 is f dash of xk. Then your xk, that is sol of k, equals to x of k minus 1 minus f1, that is f of xk, upon f dash xk. And your error I am taking as f1, that is once you get the solution, your this f1 should be 0, right? Because your sol of k minus 1 is the solution. That's why your error I am taking as this f1. It is not correct to call this as error, rather it is better to call this as the functional value. Then I am incrementing the number of iterations by 1, and then I can print it here. Yes. Solution. Solve of k minus 1. So if we run this code, you can see here your solution is 2.77 in 4 iterations. So now I will show you. 1 second, I think some mistake is there. So it should be so. Second. There's some error, I think, because it is not giving the correct solution. Just a second. Oh, this I have to take as absolute. That's why error is coming. Because it is negative, that's why it is not running. So your solution obtained is 3.349 in 7 iterations. So you can see here. Now I'll show you how this initial value is going to determine your solution. So if I change the initial value to say some big value 1000, you see your solution obtained is 15, which is another solution of this equation in 15 iterations. So if you change the initial value, it is giving you the other solution, and also number of iterations increases. So if you plot this function, you can see there are two solutions. Pt equals to equal to say 1 colon f equals to got this pt comma f x line and 0 y line. So you can see here there are two intersection points, right? One is this 3.349 which we got. This is 3.349, around 3.4, and this is around 15.1. So based on this initial value, whatever you take, the closest value to it, it will give you the solution. So first we were taking as 0, right? So closest value to 0 is 3.349. That's why it was giving me as 3.349. If I take it as some other value, say 10, which is closer to 15, it is giving you the other solution, 15.10 in 11 iterations. So this initial value, some other case I'll check, I don't know. If you take the initial value as say negative, if you take, I think, then it will not, sometimes for some functions it will not converge. Here it is converging. It will take some, I don't know. But for some functions, it will be this initial value will determine your convergence also. It is here you can see the number of iterations. It is increasing with the as you are deviating from your initial solution. But yes, sometimes it happens also that because of the initial guess of the solution, you will not get correct. You will not get a correct. You will not get convergence in the Newton-Raphson method. Is it clear? Any doubts? Okay. So now we'll move to the last topic today's, which is multivariable Newton-Raphson method. I'll just stop sharing here, share my notes. So now we will see on multivariable Newton-Raphson method. So multivariable Newton-Raphson method. So in multivariable Newton-Raphson method, again, we will have two equations and two unknowns, right? So here example I'll take. First equation is equals to 0, x power 2.4.1y. So these are the two equations which are given to you, and you are given the initial solution as 1, 1. So this is the x of 0 and this is my y of 0. So in this format, it will be given to you. Then you will be asked to find out the solution for x and y. So here the iterative formula, it will little bit, it will change. So what for single variable, what was the formula? It was basically x of k plus 1 equals to xk minus f of xk on f dash xk, right? So here what will happen is we'll get everything will be in matrix form, right? Here x of I plus 1 equals to x of I minus, we will have what is called as the Jacobi equation, the Jacobi function. Anyone of you, are you familiar with the Jacobi function? The Jacobi matrix rather, for a system of equations? So what is a Jacobian function? We need to derive from if you have a set of equations for a 2 cross 2 system, for a two unknown system, I'll first show you. So your Jacobi function is basically, suppose the first equation is f of x comma y and second is g of x comma y. So it will be dou f by dou x, that is the partial differentiation of f with respect to x. Here you will have dou f by dou y. Here you will have dou g by dou x and dou g by dou y. So now we will see here for this function, this is the general standard format of Jacobi for a 2 cross 2 matrix. If you have 3 cross 3, you will have another 3 cross 3 matrix. You will have basically first row you will have dou f by dou x, dou f by dou y, then dou f by dou z. Similarly, dou g by dou x, dou g by dou y, dou g by dou z. Then you have the third function, dou h by dou x, dou h by dou y, dou h by dou z. So that will be a Jacobian matrix. So here if we try to find out dou f by dou x first function, it will be basically minus 0.2 minus 1.5 x power 0.5 and remaining terms are of y, right? I'm just differentiating this first equation with respect to x. Now if I find out dou f by dou y, it is basically first two terms are only of x, so it will be 0. It will be dou f by dou y will be 0.4 y. Similarly, if I try to find out dou g by dou x, it is 2.4 x power 1.4. Now if you have dou g upon dou y, it is only the second and the third term, minus 0.1 plus 0.4 y. So you have your dou f by dou x, dou f by dou y, dou g by dou x, dou g by dou y. So now you have to find the values of this function at this iteration. That is, first step is, rather I will use I is 2, right? First, because I equals to 1 is the first initial which is given to you. So x of 2, sorry, x is basically here a matrix, x of 2, x of 1 minus Jacobian inverse of x of 1 into f of x of 1. So if we just find this one, this is basic, expand this one, this is x of 2, y of 2 equals to, this is basically x of 1, y of 1 minus some matrix it will come. I'm writing it as Jacobian sum A1, J11, J12, J21, J22. You have to find this out. Multiplied by this one, you have to be very careful. F of x1. So f is basically both the functions, right? So it is basically f of x of 1, comma y of 1, g of x of 1, comma y of 1. So we'll find it out each one individually. X of 1, y of 1, you know it. It is given to you. That is 1, 1, right? Jacobian we'll find out. First we'll find out this matrix, the RHS matrix. That is f of x1, comma y1 and g of x1, comma y1. So what are the equations? Basically it is 0.08 minus 0.2 x of 1 minus x of 1 to the power 1.5, 0.2 y of 1 square. Similarly, here we will get of 1 to the power 2.4 minus 0.1 y of 1 plus 0.2 y of 1 whole square. So this is the value. Now x of 1, y of 1, you know. So we can substitute it here, and I'm directly writing what we will get. Wait 1 second. we'll get minus, if we substitute x of 1 as 1 and y of 1 as 1, we'll get minus 9.92 and 1.1. So this one you have. Now your next job is to find the Jacobian matrix. So up to this, is it clear? Any doubts? Up to this, any? Okay. So, Jacobian matrix you have to find out, right? So what was my Jacobian matrix? Is dou f by dou x, dou f by dou y, dou g by dou x, dou g by dou. First, I'll write it in terms of the expressions only. What was the dou f by dou x? It is basically minus 0.2 minus 1.5 x to the power 0.5. This is 0.4 y, 2.4 x to the power 1.4, and this is minus 0.1 plus 0.4. So now you have to find out j at x of 1, y of 1, right? J at, now you have to find out j at x of 1, y of 1. So basically you have to just substitute x of 1 and y of 1 here in place of x and y. So this will come out as minus 0.2 minus 1.5, which is minus 1.7. This will be 0.4. This will be 2.4. This will be 0.3. So now in the equation you have J inverse, right? So you have to invert this matrix. If you invert this matrix, you will get minus 0.204. You can use your calculator for this. 0.272, 1.633, 1.156. So this is your J inverse. Now you have all the matrices. So my x of 2, that is x of 2, y of 2. Basically it is, I'll write it again, x of 1, y of 1 minus J inverse into f of x1, y1 and g of x1, y1, right? So if I substitute this, x1, y1 is 1, 1 minus J inverse is this one, minus 0.204, 0.272 into this one is minus 0.92 and 1.1. One second, I'll just check this inverse if it is the value which I gave is correct or not. Just give me one moment. 0.4, then it is 2.4, and it is 0.3. Inverse of it. 5, 6. Yeah, it's correct. So if we do this, this is normal matrix matrix operation, right? So it is basically 1, 1 minus this. If you multiply this, if you multiply, you will get something. I'll just tell inverse of. You will get here 0.487 and minus 0.229. If you substitute this, 1, 0.5129, 1.2. So this is your x of 2 and y of 2 matrix. So after the first iteration, you are getting this. Again, you have to repeat the same thing, x of 3, y of 3. Using in place of x of 1, again, you have to recompute your Jacobian matrix and then you have to do this whole process. So you can understand that this is a very cumbersome process, right? This is computationally very expensive. So what we do is basically, we will use our MATLAB or any programming software to do this. Is it clear? Is the concept clear? Any doubts? Any confusion,
Yes.
anyone?
Yes, and then so can you so why are we taking inverse of j? I mean, somewhat similar to the formula we developed for the single variable, and now
Yeah,
for the multiple variables here.
yeah. For the single variable, you can see here, if we write it in this form, it is basically xk minus 1 by f dashed xk into f of xk, right? So this f of xk corresponds to this f of xk. In place of 1 by f dash xk, we are using this Jacobian inverse. This Jacobian inverse is basically somewhat representative, you can tell, of the derivative of the functions, right? That's why we are using J inverse here. I think there will be some derivation for this also. I'll check it, how this J inverse is coming. So just if you compare your single variable and the multivariable iterative formula, you can find some correlation, you can at least find.
Yes. Yeah, it's clear. Yeah, thanks.
Yeah, thank you. Okay, so what I'll do is today I'll close the session. Next class I'll show you the MATLAB codes for this. So the homework for this session for the next this week is only your one question I gave, right? So this multivariable fixed point iteration method, you have to write a MATLAB code for that. Okay, fine. Then we'll meet
Can
next
you?
Friday, 6:30. Thank you.
Yeah,
Okay, sir. Thank you.
thank you so very
Thank you.
much.
Thank you,
I
sir.
have a small
Thank you.
request. So
Yeah,
can
yeah,
you
sure, sure.
suggest can you suggest some notes of, I mean, some course homepage or some very thin book? Can you suggest some reference material, I mean, which is not thick, so that I can take the printout, and so along with your notes, I can refer those, I mean, notes which are
Okay.
usually available on the different course homepages of some other professor of.
Okay, okay, I'll check that, sir. I have one book is there on numerical methods using MATLAB, but that is bit means thicker, it's a detailed thing. I'm referring that particular book only. I'll see if some smaller things are there. I'll check it.
Yeah, sure. That would be really helpful.
Yeah,
Thank
yeah.
you so very
Thank you.
much.
Thank you.
Bye. Bye.
Bye.
Good night.